Okay, we are on the topic of light, and now we're moving on to discuss color, right? So this slide here, you see a bunny, a rabbit, and what happens is the white fur, there's white light coming from the sun to a first approximation, is falling on the rabbit. All of the white light is reflected, so we see white. And over here on the black patches, what's happening is all of the light is absorbed, and so to a first approximation, no light is coming off, so this region looks black. So the same thing, if you look at a person's shirt, right? If you look at his shirt, which is red, white light from the fluorescent tube lights is falling on his shirt, and his shirt is absorbing all the different colors except for the white. Except for the red, which is then reflecting, right? Or if you look at his shirt, what happens is all the light, white light is falling on his shirt, everything is absorbed except for green, which is then reflected, right?
So in a dark room, this is probably a stupid question.
No
so
such
like
thing.
No such thing. In a dark
Extra credit
room,
to you.
Okay, thank you. So if it's pitch black, there really aren't any colors. Like it's not a specific color.
The reason why I smiled is because this is definitely a philosophical question. Mm-hmm. Where does color reside, right? And so there's a big argument about where color resides. I'm of the school that color applies to our perception. Frequencies apply to the photons. So if there were no sentient light, no beings that can perceive color, it's not meaningful to say that color exists.
I see.
Right?
Perceived. Okay.
So, and this is really interesting scientifically, that this most basic thing that we experience, we have no way of scientifically measuring or quantifying. We have absolutely no way of telling that what you see when you look at his t-shirt and you see bright pink, right? Mm-hmm. You have no way of telling that the bright pink that you see on his t-shirt is the same as the bright pink that I'm seeing on his t-shirt. Sure. For all you know, you may be looking at that bright pink and thinking it's olive green or neon green, right?
Right.
Yes. So
imagine that.
So it really is. It's a matter of faith. In other words, I could be looking at his T-shirt, your first approximation, and seeing the color that you see when you look at his T-shirt. Mm-hmm. There's absolutely no way to prove that what I'm perceiving is what you're perceiving. This is the most fundamental thing of our existence.
Well, there's people who are colorblind, so things are different.
Yeah, but all that those tests will show is that person is not able to distinguish between what you are seeing as red versus what you're seeing as neon green. Mm-hmm. But you're not able to say that what that person is seeing is actually red or not. Let's say that he is colorblind, right? And that he sees that color shirt is the same as his color shirt. All that you can tell is that he sees the same color. But you cannot tell whether he sees this color or that color, right? And this is true of all of our sensations. So the vast majority of human life is based on emotions, right? Everybody does things, buys things, sells things based on emotions. We live our entire life in a sea of emotions. We're not able to measure or quantify in any sense. There is no test, right? So nothing that, this is really philosophical, it's very, very interesting, right? The most key fundamental things of our existence are not scientifically, they're not testable, they're not repeatable, they're not reproducible, they're not sense transferable, which is, to me, is totally amazing, right? By the way, that is a bit, of a digression, but illustrating the point that you brought up. In a totally dark room, what happens is there are no photons. So if there are no photons, there's no white light coming in on his t-shirt. So he could be sitting right next to you, and there's no, his color, I mean, you cannot tell what color his shirt is. There's no light that's coming and falling and reflecting or emitting or anything else, right? Now he is, each of you is is emitting infrared waves corresponding to your body temperature. If you said your body temperature is what, 98.6? I forget what the correct number is. If we say there's 98.6, then what happens is you are emitting waves at that frequency, 98.6. Now our eyes are not designed to be able to see those waves. However, some creatures, like there are some snakes that have a special sensor that can actually sense infrared. And so it's very possible. Remember that in a previous lecture we talked about how dolphins and bats, sonar, right? They make squeaks and then they look at the reflection, and based on the reflections they're able to tell, they probably create a three-dimensional model of reality, similar to our eye models, right? Except that would have a lower resolution. So a bat can probably tell that there is a person there. If you move, you can know, right? So you can tell your general shape, but can't tell the color of your hair, or can't look at your face versus his face. And a bat can say, here's an object, here's a creature of some kind, here's a creature of some kind. And it looks like dolphins and so on can resolve pretty small fish by this. So they're even in pitch black. So they're able to create a three-dimensional model of reality based on sonar. It's very possible that these particular creatures that have that heat sensing organ may be able to create some kind of an image like that. Maybe to a first approximation, like Hollywood with those movies with those guys with the night vision goggles, that's not kind of blurred, but it's like some other color.
Right.
So you have a general sense, there's a person there, right? So it may be that that's what they are able to see. This whole field of perception is totally amazing, right? Okay, so moving on, blue glass, right? So a piece of glass that's blue, here's light from the sun that has violet, blue, green, yellow, orange, red. All of these are absorbed by the glass, and only the blue light comes through here. So when you look through there's some kind of a drink that is in a blue glass bottle, right? I forget what it's called. So blue glass bottle, some beer, whatever, I don't know. You look through, let's say that you happen to drink yourself into the bottle. Do not do this, but let's say you were, right? You happen to be inside the bottle. You just started drinking one night, and before you knew it, you were inside the bottle. I have no idea how that happened, right? So, and you look out the bottle, what happens is, here's what's happening, is white light from outside comes through, everything else comes to the glass, everything is absorbed except the blue that comes through. Right? Now, anytime light comes onto an object, like the glass in this case, some of it goes through, some of it is reflected. Let us say that this piece of glass lets only blue light through. However, it reflects an equal amount of all these different colors back out. You see what I'm saying? Certain amount of 100 units of each of these comes through. Let's say that 50 units come through here, right? So it looks blue from this side, from inside. Now 50 units of every one of these colors is reflected back out. The rest is absorbed. What color will this glass appear to be from this side? One for brown, one for pink, one for polka dotted.
All colors.
Green, white,
All colors.
rainbow. All colors?
Yeah.
Okay. Anybody else? Blue? Okay. The answer is white. Because what happens is, if it turns out that white light is coming in, and all these different rays are reflected to the same extent, it's no different from a piece of paper that I pick up from here. One of these white sheets of paper, right? What happens is, white light coming to this, okay, not that, this. White light coming to this, what happens is, certain amount of the white light is absorbed, certain amount of it is reflected. The fact that you see it as white means that equal amounts of all those different rays to a first approximation are reflected. So in effect, it's like a rainbow, except the waves all mix together in your eye. We see a rainbow, or even in soap bubbles, only because those rays are separated in location. Right? So just like this looks white, what happens is that glass would look white on one side and blue on the other. Extra credit to you if you can invent such a glass, by the way. Okay, so if you look at visible light from the sun, here's what it looks like. Brightness on the y-axis versus frequency along the x-axis. You have a distribution. The bulk of the intensity of the light is along the green and yellow, right? Region. And as you look further away, ultraviolet and so on, you can see that the frequencies, a lot of the intensity is largely cut, which is a good thing, because if we had a lot of this kind of light, we will all end up with 3-headed kids, right? And we would probably end up with multiple heads, and like Picasso, we'd all look like Picasso's paintings.
We should all look like it. What would matter?
Yes. But there's a certain amount of elegance in like having a mouth here that your hand can reach. It's going to be hard to feed yourself if your mouth is in some part of you that your hand cannot reach.
You wouldn't know any different.
You'd be dead because you couldn't feed yourself.
We would be, but the next generations would be alive, and that's what they are, and they would.
But if we're dead, we can't reproduce.
They wouldn't care.
Oh, I see. You mean if we were to produce Picasso-esque? Yes. Except that they'll all die in a generation or so, right?
Maybe.
Yeah. Okay. So brightness versus frequency, same thing. Divide things up into 3 major bands. You end up with red, green, and blue as the major components of the light, right? Oops. So going on to the next thing. If you look at the spectrum of light, here's at the very top is the entire range. You add it all together, you get white. If you cut off this region and this region, you end up with just red. If you just let this region through, cut off the top and the bottom, you end up with green. Just let the top through, you end up with blue. If you mix the red and the green, you end up with yellow, which is very counterintuitive. If you mix the, what color is that? The green and the blue, you end up with cyan. If you cut out the middle, the green, and you mix the red with the blue, you end up with magenta. Right? So this is color mixing. So if you had 3 projectors, a red projector, a blue projector, and a green projector, and each of these broadcasts sends out a circle of light, where they overlap, like Venn diagrams, where they overlap, you end up with, say, blue plus green gives you cyan, green plus red gives you yellow, then blue plus red gives you magenta. The one that's the most confusing to me and to most students is the red, is the yellow. How do you end up with adding red and green and creating yellow, which looks so different? Right? Now, interesting thing, if you try this with color paints, it will not work. It works only with emitters, with light is emitted, right?
Aren't those, I can't think of what they call that, not true red, true blue, true green, because if you mix true red with true green, it turns black. It won't let light through. I've done an experiment like this before where you take, it's a true red and a true green, and you can see through them.
Filters?
Yeah, and then you put them over each other and you can't see anything through them.
That's interesting.
And all the colors that you see and you use that they normally mix over, where they show you like red and blue makes purple or whatever, those it's not true red, not true blue.
Yeah, I'm not sure what the filters are that you're referring to. I'd actually have to look into them more.
I wish I could remember what he said about them. But.
Yeah. Now, filters and absorption is different from this particular case, but we will look at absorption as well, right? But yeah, I'm not sure what that is. Yeah, because if you had white light, and even if you were to subtract out the red, if you had totally white light, you subtract out the red and the blue, you should still end up with green.
Right.
You should have green coming through. So something strange going on there, right? Okay, so this schema, if you will, of adding colors is called the addition of primary colors. So additive primary colors, RGB, red plus green plus blue, the traditional RGB monitors, right? Computer screens, TV screens, and so on that are RGB monitors, they would actually have a little pixel. They would have a red pixel, a blue pixel, and a green pixel next to each other. The electron beam would come and stimulate each of those to give off varying degrees of light, which will then end up creating some combination of light. Okay, so introducing the concept of complementary colors, which is relevant to the question that point that you brought up. If you have a light source putting out blue light, green light, and red light, here's a golf ball, and what happens is there's a shadow here where the red light is cut out. There's a shadow here where the green light is cut out. There's a shadow here where the blue light is cut out. So the only light that's getting to this part is going to be the light from this light source as well as this light source. So green plus red will give you a yellow shadow. In this case, you're getting no light from green. You're getting a shadow where green is not present. However, blue and red are present, giving you this purpley magenta-y color. And here you end up with cyan. So any two colors, complementary colors, is a sequence of colors. Two colors where you add them together and you end up with white light, right? That will make it complementary. Okay? So in this case, complementary colors would be this magenta-ish color plus green would be complementary. Add this plus this. Take the golf ball away, you immediately, the only thing you've done is you've taken this shadow and given it yellow or the green light, and this will immediately become white, right? So this color plus this color is complementary. This color plus that color is complementary. This color plus that color is complementary. Add the two together, you get white. Okay, previous set of slides dealt with additive primary colors. Now this particular slide is dealing with subtractive primary colors. Now, what can be a little confusing to students regarding the subtractive colors is the fact that the process to create the picture is additive. So for now, let's ignore the rest of the slide. What is a subtractive color? A subtractive color is where, okay, my shirt is not helping. May I have your shirt as an example? You're welcome to give it to me at a later date too. Okay, so white light is coming and falling on your shirt, right? So the subtractive color of her shirt is blue, which means that the other colors are subtracted out. White light comes and falls on your shirt. The red is absorbed, green is absorbed, blue is the only color that's reflected. So do you see that, right? So your shirt, which is green, yes, rather than bright pink, right? So your shirt that is green, what happens is the red from the fluorescent light, the red light, blue light, and green light falls on your shirt. This is subtractive colors. So the other colors are subtracted away. Red and blue are subtracted away. Your shirt holds on to them and releases the green light. Right? This is why a black top is supposed to get hotter sooner. White light falls on her black top, and all of the light, the red, green, and blue, are all absorbed and held on. That increases the energy of the black top, and so it gets hotter. Right? On the other hand, you're reflecting 2 of the 3 primary colors. And a person who's wearing a white shirt, let's say you're wearing a white shirt. If you're wearing a white shirt, right, what happens is all the light that's falling on it is reflected off. None is absorbed. Okay. So the 3 colors of absorbing pigments. Now, so that was an introduction to the subtractive colors and the method by which an object using subtractive colors looks a certain color by subtracting out the other colors. Now, this is the process that's used to create the pictures, for instance, in your textbook. And this can be confusing for students because this is an additive process. It's not a subtractive process. What you're doing is, first, this is called 4-plate printing. You have one plate that prints this kind of reddish color, a second plate, second pass that prints this yellowish color, a third pass that prints the blue color. Right? So, if you print, so literally the piece of paper that you're seeing in your textbook would have had one printing with one color, then another printing with another color, then a third printing with another color. So once you've done that with the 3 colors, you'll end up with a picture that looks like this, which is kind of weird. Now on top of this, you print again the black color. And once you add the 2 of these together, you get what we're used to seeing in our textbooks. Right? So it's called 4-color printing because 1, 2, 3, 4. There are actually 4 passes. This is the reason why color textbooks are way more expensive than black and white textbooks, right? At least from the viewpoint of the printing process. And the same thing with other books. Okay, so the 3 colors of the absorbing pigments are magenta, yellow, and cyan. So cyan, yellow, and magenta, this is mixed, right, with multiple layering together with the black to create the final picture. Okay, now introducing the concept of scattering or radiation. If you have an atom here, a photon comes to the atom, incident beam of light coming to the atom absorbs the photon, then wiggles and sends out light in all directions. In this model is not completely correct, right? For a given atom, it sends out the light in one direction, the atom next to it sends it out in a different direction, so the average atom sends it out in all the directions, right? So that's the next level of understanding past this point. So, example of scattering is, I don't know where this picture is from, but some part, it looks like maybe China or some place like that, where you got these hills or mountains in the distance, and you can see that the sky looks milky, right? It looks milky white, and what happens is there's enough, either very likely moisture in the air, that the water molecules are scattering the light from the sun in all these different directions, causing this milkiness. So because there's a lot of water vapor between us and the mountains in the distance, more of the light is scattered.
So they're reflecting.
They are difference between scattering and reflection. Reflection is, and we'll see this in a future lecture, light ray comes in at a certain angle and it's reflected in this angle. So it's a very strict connection between the pacemaker. Very strict connection between the angle of the incident beam and the extreme, the outer. Scattering is all directions at random.
But they both are white?
So
if white light comes in, then the first approximation is white light that is scattered.
So scattering is multiple reflections happening at once. Because each ray of light is bouncing off one water molecule, making one reflection. But if you have a bunch of those going on at once, all the light is scattered.
You can look at, I'm trying to make sure that we don't confuse the two, because reflection has a very strict relationship. Light comes in this direction, it has only one option, it can only go in this direction. So if it comes into this purple binder in this direction, it has to go out in that direction. However, scattering, what happens is the purple binder can absorb the light and then send it out in any direction at once. So there's a difference between the two, right? But they're similar in some sense. If you've ever wondered why the sunset is red, right? Why is the sunset red, particularly in Arizona and so on? Here's what's going on. what happens is, here's the Earth, here's the atmosphere, and here's the sun, right? This is the shortest path. It's the path at noon. What happens is the sun rays come directly to us. They're absorbed by a smaller amount of the atmosphere and also scattered by a smaller thickness of atmosphere. As you go to a portion of the Earth where they're now at sunset, right? Because the sun is out there, here's the Earth, and here's the region of sunset. The rays from the sun coming to the Earth are traveling through a much greater width, thickness of atmosphere. So more of these rays of light have the opportunity to get scattered away. Now it turns out light, we said, has like a rainbow of colors. To a first approximation, you can think of it as red, blue, and green, right? So blue and green have shorter wavelengths, red has a longer wavelength. The shorter wavelengths are scattered more by the dust particles in the air. So they get scattered away. So what's left? What's left is the red waves. So what is left is the longer wavelength waves that don't interact as much with the particles and with the atmosphere. So they come through, and that's why the sun looks reddish from here. The same sun at the same time from here does not look reddish, because the rays that come here don't have as much of the blue and the green scattered away. So if you look at a cloud, clouds typically look, these kinds of clouds, cumulus clouds, they look white, and a cloud is basically water vapor, right? So what's happening is the molecules of water up here, the white light coming from the sun is being scattered, not reflected, scattered by these bits of water molecules. And they're being scattered in all different directions. And so you see, the sun is white, so we see it white. If the sun was suddenly to go bright blue, this would all look bright blue. If the sun were to suddenly go bright pink, this would all look bright pink. It's going to scatter whatever color the sun rays are that are coming in. On the other hand, different phenomenon. In the case of water, so let's say that you're surfing one of these huge waves, right? And you happen to be inside the wave. And you look inside the wave and you're looking through the wave. What happens is, what color does the water appear to be? Right? Cyan, kind of bluish, right? What is happening is, the water is cyan because it absorbs the red light. So red, blue, green waves are coming through the water, right? So the sun is on the other side coming through, and what happens is, the greenish is absorbed a little bit, the red is absorbed a lot by the water. So what is left is mostly blue with a little bit of green, which adds up to look cyan. That's why when you look through the water, it looks cyan, bluish. On the other hand, what you're seeing here, the froth at the top of the wave, here the wave is broken up into small little particles of water, little drops of water, and the sunlight is reflecting off of them, really scattering off of them. And so we're seeing the white associated with the sunlight, right? Yeah, it's white because, so you can see two completely different phenomena that are occurring there. Now, if we look at this, so this chapter now, we've been interested in the concept of light, and we're looking at a few different applications, if you will, or situations in which light behaves in different ways. So here's another example, the feather of a blue jay, right? You've probably seen that some birds have incredibly iridescent plumage, right? If you look at the feathers, it's not as if they've been painted with a water paint or even an oil paint. They look incredibly vibrant, right? Iridescent, yes. So here's an example where, now I cannot say from personal experience because I've never pulled one of these blue jay feathers and looked at it in a microscope, right? But allegedly what happens is, there are no blue pigments in the blue jay's feather. So it's not a blue pigmented jay. It's a blue unpigmented jay, right? So it's a blue jay sans pigment. So why does it look... It's a bit complicated too. So that's why they just shorten it to blue jay, right? Extra credit, right? So what happens is, there's no blue pigment, there's no blue paint, nothing of the sort. But what is happening is, there are tiny little cells, they're calling them alveolar cells, where they're, right, in the barbs of the feathers, and those cells are of the right dimension that they scatter blue light. So white light comes and falls on this, and the blue light is scattered in our direction. And so this thing looks so beautifully blue. So there are other birds, I'm presuming other birds that have very rich plumage. It would be interesting. Some fraction of the birds probably have pigmentation, and some fraction of the birds don't have pigmentation, but use, if you will, this method by having cells of different sizes in different places, right? So feathers with cells of this size, that size, and so on, to show off the iridescence. Cool? And I think that should end this. So a reminder for you to go ahead and do the multiple choice questions. Since today's